Hello, welcome back. Right. Um,
Nice.
so we're gonna continue with thermal properties of matter. I think we still have a couple of questions that we haven't discussed yet, so we're gonna do that. And then after that, we are going to move on to the next chapter. Okay, hang on. Okie dokie. Where is it? Uh, okay. All right. So I believe we stopped here. Question 6. So the pressure of an ideal gas is decreased at constant temperature. Explain what change, if any, occurs in the internal energy of the gas. So you have to use the definition of internal energy. I mean, there are two equations you can use when it comes to seeing whether internal energy changes. You can use internal change in internal energy is equals to the change in the kinetic energy plus potential energy of a gas, or you can use the first law of thermodynamics, with work done on the gas plus heat supplied to the gas. So one of these equations. So in this particular case, you want to use the first one because they tell you that this is an ideal gas. So for an ideal gas, the change in the potential energy of an ideal gas is always zero because an ideal gas has negligible intermolecular forces. Okay, so it's a ideal gases have, oh, you know what, let me just type it out instead of writing out this with my terrible handwriting. Oh, actually, I think I have this on my slides. Okay. Oh, okay, let me just explain what happens. So for an ideal gas, the change in potential energy is zero. So this thing is zero. And the pressure is decreased at constant temperature. Okay, so using the equation of state of an ideal gas, oh, actually, you don't have to use this. So since the question tells you that it's at constant temperature, so you can actually infer that the change in kinetic energy must be zero as well. Because remember, for an ideal gas, the mean translational kinetic energy is equals to 3/2 kBT. So if your T has no change, that means your EK must have no change as well. So the change in EK should be zero. Therefore, there is no change in your internal energy of the gas. Okay? So this is what you want to say. Kinetic energy is constant because constant temperature. Potential energy is zero because no intermolecular forces between ideal gas particles. Therefore, internal energy is unchanged. All right? There we go. Next up, the student carries out an experiment to determine the specific latent heat of vaporization of a liquid. Energy is supplied at a constant rate to the heater when the liquid boils at a constant rate. The mass of the liquid evaporated in a fixed interval is measured. The power of the heater is then changed and the procedure is repeated. Suggest how it may be checked that the liquid is boiling at a constant rate. So to check that the liquid is boiling at a constant rate, all you have to say is the bubbles, right? You make a reference to the bubbles. So bubbles produce at a constant rate, or the mass evaporates at a constant rate. And make sure that the temperature of the liquid remains constant. So that it is, boiling at 100 degrees Celsius. So why does the rate of evaporation is determined for two different power ratings? Okay, so why do we even bother doing that? What will happen if you fill a container with equal mass of ice and water and put it in 0 degrees? Well, that is a bit of a contradiction, doesn't it? Since in order for something to be at 0 degrees, okay, wait. If it is at 0 degrees in the first place, the water would be ice, not water. So you can't have. Oh wait, no, I think I know what you mean. Because when water transitions to ice, it is at 0 degrees. Would the water freeze or the ice melt? Hmm. Um, that is a good question. I suspect the answer to this question has to do with the fact that it is probably an impossible situation. But how? Let me think. Well, if you have water at 0 degrees and ice at 0 degrees, one of them would actually have more energy than the other because they are in different states. So their potential energies are different. So the one with more energy would transfer energy to the one with less energy. So I suspect what would happen. I mean, it also depends on the mass. If you only have a little bit of ice and a lot of water, hmm, 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 yeah, I don't know. I suspect this is one of those things in physics where you have like some singularity, so you don't really know what would happen at that particular instant. Um, it's a bit like, let's say, what was the example again? Right. So let's say you have a guy, right? You have a guy running at 100 meters per second. Okay, that's a bit ridiculous. Never mind. 10 meters per second. Okay, he's like an Olympic runner. Pun intended. Nice one. Nice pun. I like that. Let's say you have an Olympic sprinter running at 10 meters per second, and this guy is, let's say this is 100 meters. And then over here, you have a tortoise that is moving at 1 meter per second. Is this the example I was thinking of? Okay, so for every 10 meters moved by this guy, no, what's that? No, actually, never mind. I was thinking of something else actually. If I think of a suitable analogy, I will come back to this question. But I suspect it's one of those kind of ideal situations where it's probably not going to happen, or unlikely, or impossible to happen. So when you have something like that, you just can't work it out because that's not going to happen in the first place. But maybe there is something else at play. But yeah, as for now, I guess I don't know. Good question. I'll think about it and I'll get back to you. So why is the rate of evaporation determined for two different power ratings? So the answer for this might catch you off guard because it is to compensate for heat losses to the atmosphere. Okay, how should I explain this one? This one is quite tricky to explain. Let me think. So okay, so we know that Q is equals to L, hang on, L delta M, right? The specific latent heat formula. And we know that power is equals to this over this, which essentially is, this is P times T, because delta T is T final minus T initial, but T initial is usually 0, so we just leave this as, T. Okay, so we have PT here equals to L delta M. And, but this delta M is the amount of mass that was evaporated when it's boiling, right? But the amount of mass that was evaporated because it's boiling does not account for the constant rate of evaporation. So in fact, how should I write this? Let me think. So this delta Q is actually the heat supplied to your apparatus. So you think you have supplied 100 joules of heat, but actually what's happening is you've only supplied 90 joules of heat, and 10 joules is lost to the surroundings. Okay, so this is the heat supplied using your apparatus, and then minus the heat loss to your surroundings. So technically this is what's happening. And then this Q here is going to be PT minus Q loss equals to L delta M. So technically behind the scenes, this is actually what's happening. For an ideal experiment, we assume there's no heat loss, but technically there's some heat loss, right? So PT must be equals to L delta M plus Q loss. Like this. And then what are the variables here? So the variables are, usually when we plot the graph, we plot T and then delta M, right? So T is equals to, L over P delta M plus Q loss over P. And if you were to draw a graph, actually no, let's try to make delta M the subject. Let's make delta M the subject instead. Let me just move things around a bit. Hang on a sec. So delta M is equals to PT minus Q loss over L. So if you plot, okay, delta M is original mass minus current mass. Right? And the original mass is not changing, so the variable is actually your current mass. So your current mass is actually going to be, if I move m naught over here, it would be minus, and then I move that over is plus. M naught minus pt over L plus Q loss over L. Okay, so we have negative P over L times T plus M naught plus Q loss over L. Okay. So if you look at this, you will see that this is actually a straight line graph. If you plot the current mass against time, you would actually get a negative gradient straight line that passes through some y-intercept, and the y-intercept is going to be m naught plus Q loss over L. Okay, so the reason you are doing this for two different power ratings is because you actually have several unknowns in this equation. So let me show you the unknown. The first unknown is this Q loss. You don't know this unknown. And you don't know what the L is. Well, actually, let me think. Q loss. So you have M naught. You have M. You have T. You have your gradient. From your gradient, you can actually work out what L is because you know what P is. Right, so you know what P is, and from the gradient, you can work out what L is. So if you have L, you have M naught, you can find Q loss. Um, hmm. Hey, Danny. Hello. Okay, so what you're gonna have to do is, how should I explain this? You need to plot this graph, but in order to plot this graph, you need to have multiple points of M and T, right? So you have to, for a specific power P, you can get some line like this. And then from there, you can work out what L is, and then you work out what this guy is. Actually, let me think. Blah, 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 blah. Constant rate, motion constant rest, fixed interval is measured, the power of the heater is then changed, the procedure is repeated. Maybe if the power, okay, suppose you don't know what the power is. I think they're just trying to eliminate random error here. Yeah. So if you do two different experiments with two different power ratings, and they both pass through the same y-intercept, then you can actually work out what Q loss is. And that is the amount of heat loss. So you're trying to compensate for the heat loss. Was this the explanation? I think it is. But I feel like I might be missing something. Okay, if I can think about what I'm missing, If there's anything that's missing, then I'll come back to this. But I think this is the reason behind it. So you come across this kind of question in this chapter quite often. They ask you for why they use two different power ratings, and the answer is always the same. You just say, to compensate for heat losses to the atmosphere. You got stuck on the bathroom floor. What do you mean? Did you pour glue on the bathroom floor and then you got yourself stuck on it? Nani? State and explain qualitatively the change, if any, in the internal energy of the following system. A cylinder containing gas at constant volume is in sunlight so that its temperature rises from 25 to 35. Okay, so here they didn't tell you it's ideal gas, so you can't assume that the change in potential energy is zero. But they do tell you it's at constant volume and the temperature is increasing. So constant volume, temperature increasing. So if temperature is increasing, that means your change in your kinetic energy should be positive. Okay. Constant volume means the work done on the gas should be zero because it's not expanding and it's not being compressed. You can also assume that the heat is being supplied to the gas because it is in sunlight, so your Q should be positive. So since we have these two values here, we can actually use the first law of thermodynamics, right? So we know that change in the internal energy is equals to this guy plus this guy. And then since this guy is 0, volume is unchanged, and Q is more than 0, so the change in your internal energy should be positive. So your internal energy should be increasing. Yep. So basically just quote the first law of thermodynamics. Okay, next up, you have a fixed mass of an ideal gas undergoing some cycle PQRP, like so. State the change in internal energy of the gas during a complete cycle PQRP. All right. So if you start at P and then you go through one cycle and you go back to P, you can see that your volume and your pressure hasn't changed. Okay, so if your volume hasn't changed, that means your work done is going to be 0. And if your pressure hasn't changed and your volume hasn't changed, that means your temperature should remain unchanged as well. Because PV equals nRT, right? So your temperature depends on P and V, is a function of P and V. So since P and V are unchanged when you go back to your same position here, that means your temperature should remain unchanged as well. So since your internal energy depends on the kinetic energy and potential energy, actually you don't have to talk about that. Should we talk about that? Yeah, okay, actually we can do that. So since your internal energy depends on your kinetic energy and your potential energy, and because this is an ideal gas, right? It says here, ideal gas. So your change in potential energy should be 0 because it is an ideal gas. The change in kinetic energy will be 0 because your temperature is a function of pressure and volume, and pressure and volume are unchanged. Therefore, there should be no change in your internal energy. Calculate the work done on the gas during the change from P to Q. Okay, so you start at P and then you go to Q. What is the work done? So remember, for work done, you always use P delta V if your P is constant. So first, let's see, is P constant? Yes, because your P is not changing, right? So you can actually just use P delta V. So we start off with 8 times 10 to the power minus 4, and we end with 2 times 10 to the power minus 4, which means work is being done on the gas because it is being compressed. So if work is being done on the gas, so W equals to P delta V. What is my pressure? My pressure is 4 times 10 to the power of 5. 4 times 10 to the power of 5. Change in volume is going to be 8 minus 2 times 10 to the power minus 4. So we should expect to get a positive value because work done on the gas should be positive when the gas is being compressed. It should be negative if your gas is being expanded. If a gas is expanding. Okay, so times 6 times 10 to the power minus 4, we get 240 joules. Complete the figure below to show all the energy change. So from P to Q, we worked that out earlier. It was 240, positive 240. The signs are important here, by the way. And then, let's see. So how do you find the increase in internal energy? You can actually use your first law of thermodynamics. So U equals to W work done on system plus heat supplied to the system. So in this case, you would have 240 plus negative 600, which is negative 360. Then from Q to R, okay, from Q to R, you have these two values. So your change in internal energy would be this guy plus this guy, which is positive 720. Now from R to P, what is the work done on the gas? So if you look at the diagram, from R to P is the pressure is changing. You see, it's going from here to here, right? And because your pressure is changing, you can't use P delta V because this is only for constant pressure. So how do you even work out what this work done is? So normally, right, what you have to do is you have to find the area under the graph. So from here to here. Area under the graph. But to find the area under the graph, you need to either count the squares, which is going to take you forever, or you need the equation of the graph and you integrate. But we don't do that in A levels. So in this case, you have to rely on the first law of thermodynamics. But you only have one value, right? And you have two unknowns. Okay, so go back to this. You can see here, if you complete an entire cycle PQRP, the total change in U is actually 0. So from P to Q to R to P, the total should be 0. So if you look at this, we go from P to Q, Q to R, R to P. So P to P, right? That means this whole thing, this plus this should give you 0. So I put X over here. So negative 360 plus 720 plus X should be 0. Therefore, X should be negative 720 plus 360. So you get positive 360. Okay, so X is actually positive 360. And now you can use the first law of thermodynamics to work out the work done on the gas. So we have 360 equals to work done on the gas plus 480. So work done on the gas is going to be negative 80. Wait, no, I messed up. Negative 120. There. Okay, so if you have a negative work done on the gas, what does that mean? That means work is being done by the gas. So the gas should be expanding. So if you look at the diagram, you can see that going from R to P, your volume increases. So the work is being done by the gas as the gas is expanding. So the negative here makes sense. Okay? So that's how you complete this table. So this table is a very popular kind of question, so you need to know how to do this one. Okay, so we're done. So next up, let's go to question 10. You have an electric water heater containing a tube from which water flows at a constant rate, and water in the tube passes over a heating coil as shown below. Water flows in and it flows out at some temperature 18 here, and then when it flows out, it's 42 over here. So the specific heat capacity of the water is 4.2 joules per gram per Kelvin. Isn't X negative 360? Oh, is it? Minus, oh yeah, you're right. Oops, I messed up. It should be negative 360, which means this should be negative 360. So this guy should be 840. So this should be negative 840. There we go. Thanks for pointing that out. Okay, so next question here. Use the data to calculate the flow rate of water through the tube. So this one is a bit of an unusual question. To find the flow rate, you can just look at the units. They want grams per second, right? So what you could do is start with the equation for specific heat capacity, because that's a given. Oh, Sleepy One, welcome. Thanks for the follow. So let's say we have Q equals to mc delta T, like this. And we're gonna rearrange, we're gonna move this m over here. So we have delta Q. Wait a minute, no. Hang on a second. Grams per second. Grams per second. We're also given the power of the heater. Oh, okay, I see. So power is actually delta Q over delta T, right? Which means delta Q should be P delta T. Normally we just write delta T as T, so we just put T here. So we can actually leave this as PT equals to mc delta T, which means P must be equals to m over T, C delta T. And you can see m over T is actually mass per unit time, which is referring to the flow rate of water. So m over T is actually what we are looking for. So we just make m over T the subject. So we have P over C delta T. P is the power, which is 3,800. C is the specific heat capacity, 4.2. Delta T is the change in temperature of the water, which is 42 minus 18. You plop that into the calculator, and you're done. So you get 37.7 grams per second. Yep. 3 significant figures. And we're done. There we go. Part B. State and explain whether your answer is likely to be an overestimate or an underestimate of the flow rate. So what do you think? Is it likely to be an overestimate or an underestimate? What do you think? And why? What is the reason for your statement? Because they want you to state and explain. No reason? What? Then you're gonna lose a mark. right? Usually it's 2 marks for this. 1 mark for this, 1 mark for this. Overestimation cause of the heat loss. Okay, the reason I think is correct. Okay, let me see if it is indeed an overestimation. Physics. No, that is not an acceptable reason. Okay, so let's see. So we put in this much power, right? And we are assuming all of this power gets transferred to your water. But in reality, a small fraction of that is lost to the surroundings. Okay, so this P here is actually lesser than, is actually more than what it should be, because you're assuming that if you put in 100 watts, 100 watts gets transferred to the water. But in reality, maybe 95 watts gets transferred into the water, 5 watts is lost to the surroundings as heat. So this should actually be, this is actually higher than the actual value. Okay, which means this guy being proportional to P, so you say since M over T, or the flow rate is proportional to P, and P is higher than the actual value. Actual value is the one that accounts for heat loss. Therefore, M over T is an overestimate. So you were right. 1007 sun. Very true. Yeah. Okay. Oh, we're done. This is the last question. Oh ho! Finished. All right. So that's it for this chapter. I think we've covered everything already. So, yep. Moving on, we can do Coulomb's law. Okay, let me get rid of this. Okay, we have a bit of time, so let's start a new chapter. By the way, all the notes and stuff for the new chapter I've uploaded on Google Classroom, so you can actually download it from there. Let me just load these documents up. Give me a sec. Okay. Here we go. So, have you guys downloaded the notes? Yeah, it should look like this. Chapter 20. It's a, as you can see, it's a very long chapter. I'm not sure if we can actually finish this week, but I will try my best to finish this chapter this week. We probably can. Okay. So, in this chapter, we'll be looking at Coulomb's law. Basically, it has to do with the electric fields. So you've done electric fields in AS. We're gonna do a deep dive into electric fields. And we're going to compare that with gravitational fields from chapter 2. Okay, so from AS, what we do know is that electric field is a field of force, and you can represent it by using field lines like these. And the field lines always go from the positive charge to the negative charge, because what do the field lines mean? The field lines represent the direction of the electric force experienced by a positive charge. Yeah? The field lines represent the direction of force experienced by a positive charge. Electric force. Yeah, we did this in AS. And you know, for parallel plates, we can say the electric field strength is the potential difference between the plates over the separation of the plates, D. And the definition of electric field strength, capital E here, is the force per unit positive charge. Hopefully this is coming back. Okay, so what Coulomb's law deals with is it tells you the force, it tells you the magnitude of the force experienced by two charges. Okay, suppose I have 2 point charges, kind of like point masses, you know, but instead of point masses, they actually have charge. So you take 2 point charges and you put them, you know, close to each other. Let's say you have a point charge here and a point charge here, and this is charge Q1, this is charge Q2, and the distance between the 2 point charges is R. Then the force experienced by each of these charges would be proportional to the product of the charges and inversely proportional to the square of the distance between them. Does this remind you of something? Oh, it should, because this is very similar to gravitational force. That's right. So remember, gravitational force is actually proportional to the product of the masses over the distance between the center of masses of the 2 point masses. Okay, as you can see, they are identical. Now the difference is for for gravitational force, the proportionality constant is G, capital G, the gravitational constant. But for the electric force, also known as the Coulomb force, the proportionality constant is 4 pi epsilon naught. And this epsilon naught here is known as the permittivity of free space. It's just a fancy constant. Okay? I think the value for that is 8.85 times 10 to the power of negative 15 or something like that, if I'm not mistaken. But yeah, aside from that, they look pretty much the same. Okay, so that is Coulomb's law. However, let me just mention something real quick. For a gravitational force, masses, there's no types of masses, right? There's only one kind of mass. So masses are always attractive. They always attract each other. But charges are different, because if your charge is, if you have 2 like charges, they repel. If you have 2 unlike charges, they attract. So electric force may repel or it may attract, depending on the 2 charges. Right? Technically, masses, for masses, you actually have 2 different kinds of masses. You have matter and antimatter. But I'm not really sure whether antimatter and matter would repel. I don't think they do. they don't really behave like charges, like, light charges repel, unlike charges attract, because mass and mass attracts always. But yeah, it's kind of silly to argue about this because gravitational force is not really a thing. So Newton's law of gravitation, like I said, is not an accurate theory. You want to use Einstein's general theory of relativity, but that is a topic for another day. If you ever take up physics in uni, then you'll learn about that. But the law of gravitation that we learn is generally good enough when we are dealing with non-relativistic speeds. So relativistic means close to the speed of light. So as long as we're dealing with speeds on the planet Earth, we don't really have to deal with things moving at the speed of light or close to the speed of light. So Newton's law of gravitation is a pretty good approximation of what is actually happening. And it's a lot easier to work things out using the law of gravitation rather than general theory of relativity. Anyway, it's a bit like the binomial theorem, right? If you are trying to expand something with some integer power, you're going to use the regular binomial theorem and not the general one that we learned in A2 math. So kind of the same analogy here. Anyways, electric field strength. So we know that this is actually referring to the force per unit charge, positive charge. And this symbol's E, and this is the unit, right? This is all very familiar. And if you were to draw the gravitational field strength, small g, this is actually a small g here. You probably can't see it because it's really small. Maybe I'll zoom in. Right, so if you plot G against R, G equals to Gm over R squared. Remember this from chapter 2? So G is proportional to 1 over R squared. So if you were to plot G against R, you would get a graph that looks like this because you're plotting 1 over X squared, right? And that's what it looks like. Now for E, which is the electric field strength, so we know that the Coulomb's, from Coulomb's law, that electric force is actually Q1, Q2 over 4 pi epsilon R squared, right? And we know that the definition of electric field strength is force per unit charge. So if we put in this guy here, we're going to get Q1, Q2 over 4 pi epsilon R squared over Q. So which Q is this Q referring to? Is it Q1 or is it Q2? It depends on which charge you are referring to. So let's say I have Q1 here and I have Q2 over here, right? And I want to find the electric field strength due to Q1 on Q2. So due to Q1 on Q2, which means I'll have to divide this by Q1. So I'll cancel this, and then I'll get Q2 over 4 pi epsilon R squared. Due to Q2 on Q1. I mixed it up. So if you are trying to find the electric field strength due to Q2, then you have to divide by Q1. If you want to find the electric field strength due to Q1, you have to divide by Q1. Divide by Q2. Okay, so this is actually referring to the electric field strength due to Q2 on Q1. So this is what you would get. Okay, so whether it's 1 or 2, it depends on which one you are interested in. Okay, so the point is, Q2 can be either positive or negative, right? So if Q2 is negative, then you're plotting a y equals to negative 1 over x squared graph. If Q2 is positive, then you're plotting y equals to 1 over x squared graph. That's why your graph could be either this red line here if it's positive, or this blue line here if it's negative. And remember, E refers to the force per unit charge. So if your electric field strength is negative, that means you just experience a force in the opposite direction. So we'll talk about this in more detail later when we draw all the graphs out. But I just wanted to show you that there's this little difference between the two. Okay, because this charge can be positive or negative. Okay. Next up, we have something called the electric potential. The electric potential is the work done per unit positive charge in bringing a small test charge from infinity to a point. So this would probably be quite familiar to you since we've done this in chapter 2. Gravitational potential is the work done per unit mass in bringing a small test mass from infinity to a point. So I've just replaced charge, positive charge, with mass. And then that's how you get, gravitational potential. And the symbol is the same, we just use V. And again, it's a scalar because electric potential, gravitational potential, they're always scalar because it's work done. Work done is a scalar. Okay, good. All right. So, okay, how should I explain this? Let me think. So, back then in AS, we did potential difference, right? So, potential difference was defined as the work done per unit positive charge. That was the old definition. But now that we have actually learned what electric potential is, what potential difference actually means is the difference between two locations if you were to bring a charge from infinity to those two locations. So let's say I have a charge at infinity, and then I have two points here on a circuit, right? So let's say I have a circuit, there's a resistor, and then like this. And then maybe this is position A, position B. So if I bring a charge from infinity all the way to position A, maybe I need 100 electron volts. And if I bring this same charge all the way from infinity to position B, maybe I need 95 electron volts. Oh, so the difference in the potential is going to be 5 electron volts. So that's your V, your potential difference. Right? So the potential difference and potential are different things. That's why here I have a delta V, because we are referring to the difference in the electric potential. So this is just a conceptual difference that you need to be aware of. Okay, that's it. So, right, how do we write electric potential using Coulomb's law? So we know by the definition of electric potential, well, technically potential difference, it is actually work done per unit charge, right? So in the context of A-level physics, they don't usually write potential difference with a delta here, even though they actually mean potential difference. So I'll just get rid of this. So we know potential difference is W over Q. W is actually force times distance over Q, like this. And F, we can replace that with Coulomb's law, which is Q1, Q2 over 4 pi epsilon R squared. This whole thing is multiplied by R over Q. So we get rid of one of these R's, get rid of one of these Q's. So you can either get rid of Q1 or Q2. It depends on which one you're interested in. So eventually you get Q2 over 4 pi epsilon R. Or it could be Q1, whatever. So that is the expression that you would get for electric potential. Okay, so far we've done 3 things. We've done electric potential, electric field strength, and Coulomb's law for the force, electric force. So we've done 3 equations so far. Okay, and again, electric potential can be drawn like this or like this, because it depends on whether the charge is positive or negative. For gravitational potential, it is always going to be this one here, because remember, gravitational potential, also written as psi, is negative gm over r. So you're always plotting like a negative 1 over x graph. Okay, so all this will be important later when we talk about drawing graphs. For now, just bear that in mind. Okay, so if you were to draw, okay, before I explain this, I should talk about the nature of potentials in physics. So in physics, things tend towards a region of lower potential. Okay, so positive charges, masses, they always experience a force towards a region of lower potential. If you have a negative charge, the negative charge would experience a force towards the region with higher potential. That's just the way physics is structured, right? It's a bit like in maths, you define 1 plus 1 is 2. If you take 0 plus a number, you will get the same number. So when they came up with these equations, they came up with this convention that things tend towards a lower potential, and then they sort of made the equations around that. Yeah, kind of like an axiom. Yeah, it's kind of like the building blocks of these equations. So they made that assumption, and then they built the equation based on that assumption. So for charges, positive charges and masses, they always tend towards a region of lower potential. So masses always want to go towards a region of lower gravitational potential. And then if, let's say, I have, how should I draw this? Okay, so if you look at this graph here, right, this is for electric potential. V is electric potential. So electric potential is Q over 4 pi epsilon r, right? So if your Q is positive, then you would get this orange line here. Okay, so there's a positive charge right here. This is your positive charge. And the variation of the potential in the region near the positive charge is going to look like this. So if you look at this point here, a distance this away from the positive charge, it will have this much electric potential. If you get closer, the electric potential rises. Okay? You can think of the electric potential as just some numbers associated with a space. Yeah, that's pretty much it. It's just a number associated to a point in space. Okay? So the significance of this number is if I were to take another positive charge, I'm going to use red for this one. Let's say I take another positive charge. This is another positive charge. So this positive charge is going to experience a force towards the region of lower electric potential. And if you look at this graph here, which part of the graph has a lower electric potential? Well, it's going to be this part. So it's going to experience a force to the right. Okay, so if you put this positive charge even closer to the original positive charge, it's going to experience a larger force because it's because this is, how should I say it? Because the gradient is steeper. So you can also think of it as the gradient is proportional to the force experienced by the charge. Okay, so dV/dr is proportional to the force. And you can actually prove this using math, right? So let me show you. Let's say we have V. What is V? Okay, we know V is Q over 4 pi epsilon r, right? So if we differentiate V with respect to r, what are we going to get? We are going to get negative Q over 4 pi epsilon r squared. Okay, so you can see Q 4 pi epsilon r squared is actually your force divided by your charge, because your force is 2 Qs. So you get force over charge. And you can see here that your force is proportional to the negative of the gradient, negative of the potential gradient. I actually forgot to put a negative here. There we go. So you can see here, my potential has a gradient that's, some negative number. So the force I experience will be some positive. Positive is going to be in this direction. So positive is this direction, negative is this direction. So depending on how steep the potential gradient is, the force would be greater or lower as well. Okay, there you go. So the closer you put the positive charge to this positive charge, the steeper the potential gradient is going to be, and the greater the force is going to be. And the force is going to be pointing to the right because the right region has a lower electric potential compared to the left region. So if you think about it that way, then this graph would make sense. Okay? Now, if I have a negative charge, remember negative charges always move to a region of higher electric potential. So your negative charge would actually go this way. It's going to go up this way. And for a negative charge, if you put it in this equation here, you see that the Q being negative is going to flip the sign, right? So my force is going to be positive, which means, my force is going to be in the other direction. It's going to be this way. So your negative charge is going to experience a force towards the positive charge. Or in other words, it's going to move towards a region of higher electric potential. Okay? Now, if you were to replace this positive charge with a negative charge, okay, if you replace this with a negative charge, then it's going to follow the green graph down here. So the electric potential is going to look like this. Because my Q is going to be negative, which means we're plotting a y equals to negative 1 over x graph, which looks like that. So if I put a positive charge in the vicinity of the negative charge, it's going to be attracted to the negative charge because this region on the left has a lower electric potential. See? Yeah, if I put a negative charge, the negative charge is going to be repelled because this region has a higher electric potential. So there you go. Now, if you were to plot this in three dimensions, because we're only plotting this in 2 dimensions, you can sort of imagine this as like a cross section, right? But if you plot it in 3 dimensions, you would get something that looks like this. And so in the middle of this guy here, you actually have a positive charge. This is actually a positive charge. And over here, you actually have a negative charge. Right? So positive charges would give you like a potential well that looks like this. A negative charge looks like a hole. Right? And the gradient tells you the magnitude of the force on a test positive charge. So whenever you see potential wells, it actually refers to this diagram right there. You wouldn't see potential wells in A levels, don't worry. This one is actually for university if you get to that point. So that's what a potential well refers to. So if you were to put a positive charge here in the middle, depending on the gradient of this point, it will either go up here or go down here. Okay, so if you have a positive charge, you can sort of imagine this to be like an actual sculpture, and then you just put a stone here. In which direction is the stone going to go? It's going to roll down here. So it's going to fall down this way. So that's also an analogy you could use, but only for positive charges. All right, so that's it, really. Now, if you have, okay, so this is a cross-section of 2 potentials. So one, you have a positive charge over here. This is a positive charge. And one, you have a negative charge over here. Okay, so if you put 2 of these charges close to each other, you can see that this blue line refers to the electric potential variation of this guy here, and the red line refers to this guy here. So when you put them together, they would actually sort of stack on each other, superimpose, and then you get a superposition of potentials, which look like this purple line right there. Okay, so how do you get this purple line? You get the purple line by adding the potentials of these two separate graphs. So for example, here you can see this one is actually, let me just zoom in a bit. Let me zoom in. Oh. Okay, so you can see here, let's say it's -10, and then maybe here is +3. So when you add these two together, you're gonna get -7. Okay, and then you can see in the middle, it's like -5 and +5. So if they add up together, you should get 0. So if you look here, in the middle is 0. And then these ones, you get something like that. So whenever you want to find the total or resultant electric potential, you just add them up. Another reason is because electric potential is a scalar quantity, right? So it's like I have 2 kilograms and 5 kilograms. Masses are scalar. If I add those two together, I get 7 kilograms. So it's the same thing, because electric potential is a scalar and you want to add them up to find the total. You just simply add them up. You don't have to care about the directions or all that, because there's no direction. You just add them up. So we'll do some questions about this later down the road. But for now, just know that you have to add up electric potentials to find the resultant potential. Okay? Next up, we have electric potential energy, which is the work done in bringing a positive charge from infinity to a point. So you can see this is very similar to gravitational potential energy. So if I want to write gravitational potential energy, all I have to do is replace positive charge with mass. Done. Okay, there we go. So what is the expression for electric potential energy then? Well, electric potential energy, we can either use EP or we can use U. It's up to you. I'm going to write U, okay? U is going to be the same thing as work. Work is actually force times distance. Force is actually Q1, Q2 over 4 pi epsilon r squared times r. So one of these r's cancel. So there we go. That's our expression for electric potential energy. That's how I remember it. You don't have to memorize everything. You just have to remember the definitions. But this one you should know because you've been doing this since AS. So that's how I remember it. And that's how I recommend you remember it as well. So we've done 4 things, right? Electric potential energy, electric potential, electric field strength, and electric force. Okay, so I think we are going to stop here for today. And we're going to start with some questions next class. I think we should be able to finish this chapter in 2 classes. So let me just recap, right? So U is this guy. V electric potential is Q over 4 pi epsilon r. Coulomb's law is Q1, Q2 over 4 pi epsilon r squared. And then we also have electric field strength, which is Q over 4 pi epsilon r. There we go. So these are the 4 things that you need to know for now. There. So for today, you can try doing some of the questions for the last chapter, thermal properties in matter, of matter, and see if you can work out those questions on the past years. And then if you have any questions, you can ask me next class, or you can send them to me, because technically we still have about half an hour-ish to go, right? So I'll stick around. If you have anything, just ask me. And I shall see you, is it tomorrow? Yeah, I'll see you tomorrow. Tomorrow and Friday. So Friday will be our last class. Yep. Okay. Bye-bye. Latest.